Welcome you all to the new course on topological data analysis. The main objective of this course is to get a familiarization with the basics in topology that are useful for computing data and to master some algorithm for computing like topological persistence, homology cycles, etc. from the data, and how to interpret topologically a given data and to have a research background on the developments in topological data analysis. So in this course, first we will discuss some basics of topology such as distance, metric spaces and its examples, open and closed sets, continuity, compactness, connectedness, etc. All these are fundamentals of topology. And we will discuss some fundamentals of algebraic topology, which is very essential to understand topological data analysis. This includes homeomorphism, homotopy, fundamental groups, etc. Specific topics to topological data analysis are different types of simplicial convexes and homology, and homological groups, topological persistence, barcodes, etc. This session is to give a brief introduction of topological data analysis. If you have a data, you can interpret many things on it. Topological data analysis deals with the shape of the data. Data has a shape and shape has some meaning. This is told by Gunnar Carlsons. This course is all about clearing these two concepts. Data has a shape, and what is the shape of data? Shape has a meaning, and what is that meaning? After the course, all will get an idea about these statements. In topological data analysis, we apply topology to develop tools to visualize data and for studying quality features of data. So in this course, first we will discuss what is topology. Whatever be the concept, it is easy if you know its geometrical interpretation. So we will first have what is topology and what does the word topology means. Topology is derived from two Greek words, topos, meaning surface, and logos, meaning study. The word topology is from two Greek words, and topos means surface and logos means study. Thus from this itself you can clearly see literally topology means it is study of surfaces. So from this we can understand that topology is a sort of geometry. It means topology is somewhat a type of geometry. So what is a geometry? In geometry, we deals with concepts like the area, volume, and curvature, etc. We are not studying about the color, smell, taste, etc. Why it is so? In geometry, we are studying about geometrical property. So what is meant by this geometrical property? In geometry, we deal with the things like area, volume, and curvature of the objects under study. These are among the geometrical properties. But if I have two triangles, A, B, C, and E, F, G, AB is equal to EG, BC is equal to EF, AC is equal to GF. So these two triangles are congruent. That means the area will be equal. Area of triangle ABC is same as area of triangle EFG. Perimeter of triangle ABC is same as perimeter of triangle EFG. But we can color triangle ABC with the red color, but the color of triangle EFG need not be a red color. So this means perimeter, area, curvature are all preserved under congruence. Color is not preserved under congruence. That is why it is not a geometrical property. So exactly on what basis one call certain properties as a geometry and others as not? So a vague answer to this is properties which ultimately depend only on distance between various points of the object. So can the above criteria be made precise? We told it depends only on the distance between various points of the objects. Can this criteria be made precise, more precise? So two things are congruent if you can lay one on top of the other in such a way that they exactly match. So when you're using the terminology of function, we can state that two objects A and B are said to be congruent to each other if there exists a bijection from A to B which preserves all distance. Such a bijection, when it exists, it is called a congruence, or it is also known as isometry. So for example, the property of being isosceles is preserved under congruence. The color of an object or a smell are not preserved under congruence. So since congruence preserves distance, it also preserves anything that ultimately depends upon distance. So the geometrical properties are properties which are invariant under congruence or isometry. So these are properties which are invariant under congruence. Thus area, volume and curvature are all examples of geometrical properties, while color and smell are not. And what is this congruence? When do you say that two objects are congruent? Two objects are congruent if and only if there are an isometry between them. Two objects are congruent if there exists an isometry between them. There are different groups of isometries. The set of isometries actually forms a group, and it is actually a transformation. So what are these transformations? Suppose I have a triangle ABC. And this is triangle EFG. But how I have got triangle ABC and triangle EFG? This triangle ABC has just translated some distance to this form. So I had got a triangle as EFG. So this is one of the transformation. This is the idea behind translation. Similarly, the rotation case A, B, C. I'm rotating, it remains as a congruent. EFG, these two triangles are congruent to each other. Suppose if I am reflecting, this is ABC, BCD is a rectangle, I'm reflecting. So two objects A and B are said to be congruent to each other if there exists a bijection f from A to B which preserves all distance d of xy between f of x and f of y. That is d of xy is equal to d of f of x, f of y. So we have gone through the different group types of transformations, that is translation, rotation, reflection, and these combinations can also happen. So geometry is the study of properties which are invariant under the action of this group of isometries. So to this transformations, if we are going to include stretching or blowing, shrinking, bending, all the type of such transformations, if we are including to these transformations, what happens? That is, to all these transformations, we are going to include stretching, blowing, shrinking, bending. All type of such transformations. So our group G now becomes a bicontinuous transformation. This G becomes a bicontinuous transformation. This geometry is called topology. So in topology, we study the properties which are invariant under the action of this group of isometries. This bicontinuous transformation means what? If we can do one way continuously, we can do them the other way also continuously. That is, if f is a continuous function, f inverse is also continuous. Suppose if you have a rubber band with you, if you are stretching it, if you are leaving it, it comes to the same position. If it in the form of a circle, if you are stretching it, it can be made into any other shape like square. Anyway, you can make it into another shape. But if you leave it, it becomes to the same shape, circle. So you have stretched a rubber band to some other shape, and when you have shrinked it, it has come to the same form. So if we can do one way continuously, we can do the other way also continuously. That is what meant by bicontinuous transformation. So in topology, actually we study the properties which are invariant under the action of this bicontinuous transformation. And this bicontinuous transformation is what known as homeomorphism. This bicontinuous transformation is known as homeomorphism. That is, f is continuous, f inverse is continuous, and f is a bijection. So a homeomorphism from A to B is a bijection from A to B such that both f and its inverse are continuous. So in ordinary Euclidean geometry, what we have discussed earlier, that is geometrical properties. Geometry is a geometrical properties study. In that, we can move the things around and flip them over. That is, translations can be done, rotation can be done, reflection can be done, but you can't stretch or bend them. So this is called congruence in geometry class. There is two things are congruent if you can lay one on top of the other in such a way that they exactly match. But in the case of topology, to these transformations you are adding some other transformations such as stretching, bending, blowing, etc. So if you are getting a continuous form, you can have the other way also a continuous map. That is what we call it as a homeomorphism. So topological properties are properties which are invariant under this bicontinuous transformation. And topology is the study of this topological property. So geometry means it is a study of geometrical properties. Geometrical properties are properties which are invariant under congruence. Thus congruence is in the geometrical form. The transformations coming under geometry are translation, rotation, reflection, and their combination. To this we have added some other transformations and we have got a bicontinuous transformations form. So topological properties means that which are invariant under bicontinuous transformation. So topology means it is a study of topological properties. In topology, any continuous change which can be continuously undone is allowed. That is, a circle, in the case of geometry, a circle or a square or a rectangle, they are not equivalent. But topologically, they are equivalent. So if the circle is same as a triangle or a square, so because what you are doing, as I have told about a rubber band, the circle to make the corners and I can make into a square. Similarly, if I shrink it, I can make into a circle. So topologically, it means they are equivalent. Topologically, they are equivalent. So in topology, we study the properties which are invariant under the action of group of homeomorphism. So in another way also we can define what is topology. Suppose if I have taken a balloon and I have put a point on that balloon and I have drawn a circle around the point. Circle around the point, such as the point lies inside the circle. Now blow the balloon. Now we are blowing the balloon. Even though after blowing the balloon, the point lies inside the circle. The point will not come outside unless otherwise it breaks. So the point lies inside the circle. Even though after blowing, the point will not go outside unless otherwise it breaks. So while breaking, what is happening here? We are losing the property. We are losing the property. The property will get loose. So by breaking, what we lose it is connectivity. What we lose it? Connectivity. So topology is also considered as a tool of connectivity, the geometry of connectivity. So in many ways we can geometrically define topology. So topology means it is a study of topological properties which are invariant under homeomorphism. It is also known as a geometry of connectivity. So such we can derive many other definitions for topology. So I told a circle is topologically equivalent to a square. In this way, if you are considering this continuous deformation, this is think it as a donut, or this actually a form of mathematics form. Think it as a donut. I'm changing, giving a continuous deformation. Here, it is important that the connectivity should not be gone. That is, it should not break. So this, by topologically, we can say a donut is equivalent to a cup. And likewise, here this is sphere form. This is they are equivalent, but this is not. They are not equivalent since there is a hole in it. So continuous deformation of one object to another without breaking, that makes the topologically equivalent. So circle is topologically equivalent to a square. It is topologically equivalent to a rectangle, any other form. But the deformation must be in such a way that it should not leave its continuity. It should not give up its connectivity. So here, this circle, they are not topologically equivalent to this curve because it's actually a break has happened. They are not topologically equivalent. So this is the geometrical interpretation of topology. This is just a brief introduction to topology. And this section I am not moving on to the topological data analysis. In the next section we will discuss, we'll start with just topological data analysis and the basics which are required for topology, such as distance, metric space, open and closed sets, interior of a set, interior points, exterior points, closure, etc. These are some of the basics which we require for topological data analysis. So this is just an introductory video. In the next video onwards, we will discuss more about topological data analysis. So thank you.